right, hi, I'm Richard Crowley, and I work at OpenDNS. We're a consumer-facing company that does DNS instead of Comcast or AT&T, and we like to think we do a little better job with it. When I started at OpenDNS, we did about 8 billion queries a day. When the stat system I'm talking about today launched, we were doing about 10 billion, and just last week, we got to 14 billion queries in one 24-hour period. That's 162,000 every second. And every request gets logged, and the log lines look a lot like this. They've got a big, ugly timestamp, format, the client's IP address, and some flags and little bits that we use to determine how the query was handled, and of course, the query itself. We can't use log files to make our users happy, though. We need to make graphs. We need to aggregate so that they can see the forest for the trees. So on the left, we've got a top domains page. It's got all of your domains you've requested, how many times you've done it, and you can look at that over the last 30 days. On the right, a graph of total requests. Same thing that we show you every day, how many requests you've done. Many networks can see the unique IPs that have visited domains on their network and kind of dice things up that way. And this is useful output for our users. This is how networks can see what people are browsing on their website, on their network. Schools use this to kind of monitor and react to potential problems since they have federal regulations about protecting children on the internet. People like you and me use it because we love data porn. I interviewed at OpenDNS thinking that I'd have questions about BGP and DNS and networking and stuff like that, and they actually just asked me one question, which is how would I build the stats system? And my answer, being a hardware designer by education, was that it's going to be sort of a pipeline design. And since the data is kind of by definition partitionable, since we're taking all of these queries and giving them to each user individually, it looks a lot like MapReduce. So the pipeline is going to do 2 stages of work. One kind of looks like map, and it's bucketing by the user's networks. And stage 2 is aggregating and storing data. And the reason that I did this 2-stage pipeline is to create 2 different planes of horizontal scalability. The stage 1 needs to scale with the number of DNS requests we're doing. So when we add more DNS capacity, bring a new data center online, we need to add capacity to stage 1 to be able to bucket and process and throw out some of those DNS queries. Stage 2 needs to scale with the number and the size of our users because it's dealing with the actual storage. John Alspaugh likes to talk about Flickr's data set scaling with the number of photos per user, and we kind of similarly can scale our data store with the number of domains visited per user. We prefer to duplicate data rather than omit data, and this doesn't seem like a big deal when you're talking about Google, because what's another 3 queries to Google? But let's say you're looking at Facebook.com, or sorry, not Facebook.com, something you'd block. Let's say Playboy.com. You go to Playboy once, and you should really know about that on your network. So we can say that you went there twice, and that's OK. But saying that you went there 0 times, leaving it out, is not really acceptable. So we prefer to duplicate data. And then the last thing that we talked about in the initial design was giving each user their own table, which has nice properties for being easier to migrate users from one server to another, makes it easy to keep whole networks in memory for people that click the refresh button a lot. And it kept the primary keys smaller. It made more sense from the beginning. So I took the job, and we started to really design this system and looked at some alternative technologies like Hadoop, like HBase, and all of these kind of had some shortcomings. There were not any great data storage options besides MySQL, in my opinion. Hadoop and HBase were excellent for doing the computation, but had too high a latency to really serve a dynamic website directly from there. So we stuck with MySQL. There were still some gotchas, though. Number 1 is that we're dealing with all the domains on the internet. So we have to store them all so that we can show them back to you on the website. You don't want a 256-character varchar as your primary key. That is a terrible idea. Auto-increment, however, to just store a lookup table of domains isn't much better because even in InnoDB, the auto-increment makes a table lock whenever you insert. So we use the SHA-1 of the domain as the primary key. And this lets us, since the data determines the primary key, we can use insert ignore and basically get as much performance as we can kind of in a write forward, always sequential writes. And at our data set right now, which is about 96 gigabytes, it's 878 million domains, it's effectively write-only. We get 98% hit rate in 28 gigs of memcache. The next, my title's gone away. The title's supposed to mention something about the standard bad alloc exception. This is our next problem. When you aggregate things in memory, you're going to run out of memory. So the bad solution to this problem is to try to kind of guess how much memory you're using. And unless you're writing your own data structures, that's not feasible. The better solution is to catch exceptions when the standard template library can't allocate memory, catch the zero return, the null pointer from malloc, and deal with it. And I choose to shut down the server in a controlled way and let supervise restart it. The catch to this, I guess, is that you need to be able to actually run out of address space rather than have the kernel's out-of-memory killer come along and just kill your process. So to get to this, our ops guys like to run 32-bit processes on 64-bit CPUs. So I run memcache and the stage 2 process kind of next to each other and use all the memory up that way. Number 3 was open tables. Since we're giving all of our users their own tables and they're my ISAM, we have the table cache to contend with. And strace kind of led us to the fact that we're using all of our time opening and closing tables. So after we observed this problem, we recovered from it since strace crashed MySQL and ended up altering MySQL dsafe to keep a whole lot of tables open. And this isn't so bad in the case of a crash because the vast majority of your tables aren't actually mid-write at the time. So even though lots are marked as crashed, very, very few are actually corrupted and crashed. And this last false start, I'm calling a false start, even though it's kind of in progress. My ISAM's kind of busting at the seams, so I'm looking to change some of, if not all of the tables to InnoDB. By diverting some production traffic to a dev database, I'm seeing almost a 2x write throughput improvement. I think a lot of that is due to using the InnoDB flush log at transaction commit setting set to 2, which only runs fsync every second rather than after every transaction. That means I might actually lose a little bit of data in a crash, but the way that we play chunks of SQL into the database means that when that type of failure happens, we'll replay the entire chunk. We prefer to duplicate data than omit it, so that is less than optimal but safe. So after all of that, here is what's been running in production for the last 8 months. From a high level, and I want to focus on the fun parts, so I'll go through the life of a log line pretty quickly. Our resolvers all over the world log DNS requests, and they're pulled by the stage 1 machines. There's 3 of those running in San Francisco. And using the help of the user database, those kind of route requests to stage 2 where the actual aggregation is done. And eventually, those log lines that end up in stage 2 are written out as SQL files, again, queued to disk, that are then inserted into the databases, all running MySQL. The website in Palo Alto, OpenDNS.com's in Palo Alto, uses a proxy in San Francisco to talk to the database, and it has its own little JSON API, and that's how our stats actually get to the database. The stage 1 stage, the map stage, starts by rsyncing log files, and we use the remove source files option to kind of make sure that things are always queued on disk in one place. And then when it's processing each of these files, it's using the globals, the PHP process, it's using memcache, and finally, it uses the domains data, or sorry, the user's database to figure out where to route that particular log line. It writes them back to local disk to wait on stage 2. And one of the cool things that we do from stage 1 is we also fork out our global system-wide metrics that we use on system.opendns.com, and we multicast every single log line into a private VLAN that we have a few boxes that can just listen to a fire hose of DNS requests. And as long as you don't touch disk, you can actually get through and do cool things with the entire 14 billion requests a day. Stage 2 is the complicated fun part written in C++, and it does the aggregation so that MySQL doesn't cry when you try to insert so many billions of things into it. So here's a couple of the data structures it uses. The top one is pseudocode for a giant hash map of hash maps that's keyed by the database server that's kind of the destination for the logline, the network ID that performed the request, the date that the request was performed, and then the real meat of it is in there. There's a last updated pointer, which we use to determine when we prune the tree, and I'll talk more about that in a moment. A set of file pointers that do reference counting so that we can determine when it's safe to delete those files that are queued on disk. And then the top domains, request types, and unique IPs are the types of stats that we're recording. Those are all an unsigned int pointer that's got 24 slots, one for each hour in the day. And we store data that way so that we can select 2 rows and then for any time zone in the world work out what a day means in that time zone. The reference counts are all pointers to character, which are in this bottom structure that's another hash map. And this uses the value uses a pthread, which determines if the file has an owner, and it uses a reference count for the number of nodes in that top data structure that are holding on to it. That's how we know when it's safe to remove a logline, when the reference count is 0, when there's no owning thread. And so this reduced process that's using these data structures starts out again by rsyncing its files across from stage 1. It has 8 aggregator threads that are writing data line by line into that data structure. And then it has 8 pruning threads, which are kind of taking data out of it. And they're trying their best to remove things that are old, that have a last updated timestamp of preferably several hours old. They try to remove things that are very big, which means both the hash maps inside, like top domains, have a lot of rows in them, and that have a lot of files that could be deleted if that day was written out to disk. So it tries to keep the queue as small as possible. The kind of corner case is when standard bad alloc has been caught. Remember, that was one of the things that caught me up in the beginning. It starts to controlledly write everything out to disk as quickly as possible so that all the files that it's got in memory can safely be deleted, but the process can also end. The pruning threads, to make that possible, don't actually allocate any memory. They keep a bunch of buffers set aside and recycle them every time they run so that they can buffer SQL statements and create things that get written to disk and then start immediately over again without without allocating any memory. And then all of this has to end up in the stats databases, which right now are running MySQL 5077 and will soon be running MySQL 5077 Percona, which gives us an interesting new parameter, the InnoDB dictionary size limit. In stock InnoDB, the dictionary, the data dictionary, which is the definition of all the tables and their field types and index types, that will grow without bound forever, which is one of the main reasons you can't use InnoDB with large numbers of tables. The Percona people have been very nice and added a flag so that you can turn this into an LRU cache, which means you can use InnoDB with very large numbers of tables, and it works very well. I don't know yet whether it's good to use the table space or file per table. That's one of the things I need to decide before everything gets finished up. And it's running with table cache equal to 300,000, which, with the ulimit setting I mentioned before, allows us to keep most everything open and keep the users pretty happy. And the last bit of it is our website, which runs in Palo Alto. So we have a JSON API that runs in San Francisco to proxy everything to the website. The reason that that needs to exist at all is that the queries get run with no limit, and a lot of computation's done to kind of pack them down into the final data structure, which we paginate into Memcache with a 1-hour TTL. This means that we can do the query one time and kind of pay that expensive price once, and then all of the subsequent pages on your stats pages are going to be pretty fast. And that is the end. If we've got 8 seconds for questions, hurry. Yeah. Mm-hmm. By the end, it is SQL statements. At the beginning, it's those log lines that were the gibberish on the second slide. Well, the queuing to disk in the beginning, and actually all of the queuing steps are all sequential I/O, so that's pretty fast. The entirety of OpenDNS log lines churns out about 800 megabytes to a gigabyte of log lines per minute for the whole system. So with 3 servers, they're not saturating in any individual server's sequential I/O capabilities. It's the random I/O in the databases that really kills us. Any others? I think Adam's up now. Thanks, everybody.